All right, let's go ahead and pick up where we left off. So we're still looking at different geometry pumping units. And we've seen conventional pumping units and the Rotoflex style, the linear tower. We've also seen Mark II pumping units, the grasshopper. We've seen beam balanced. We've seen air balanced. We've also seen linear hydraulic. And what I want to look at on this slide is the reverse Mark pumping unit. But I'm going to show you a conventional pumping unit. We didn't see it from the side, and I want to show this in comparison to the reverse Mark because they're quite similar. This is three beautiful ladies up here in North Dakota in a very scenic setting right here, but these are conventional pumping units. Now look at the reverse Mark. What is the difference between these right here? They're quite similar, but there is a distinctive difference. And what you want to look at is where is that equalizer bearing in relation to the output of that gearbox. Okay, so you can see on this one right here, here's the output from the gearbox, and this is pushed forward. And that is going to be one of the most distinctive features between a reverse Mark and a conventional style pumping unit. So here are some more reverse Marks. Again, you want to look for the gearbox shaft, the output from the gearbox. Here is the equalizer bearing. It is pushed forward. And as a result of this, pushing this forward, this is going to create a different velocity profile. This type of unit is going to be kind of halfway between a conventional unit and a Mark II pumping unit, the grasshopper. So it is going to have a faster downstroke and a slower upstroke. And this is going to reduce some of the gearbox loading, just like it does for the Mark II, but it's not as severe as the Mark II, or the differences are not as much as it is for the Mark II. There are advantages to this type of unit. Mark II has some disadvantages due to its unusual geometry. These type of units do not necessarily have that, especially when you're pulling the particular well. So as mentioned, these units have a slower upstroke and a faster downstroke as a result due to pushing up the equalizer bearing up here. And on these units, they have a preferred direction of rotation, just like with the Mark II. So the Mark II, it is only supposed to go counterclockwise. The reverse Mark, if you look at the name, this is probably not why it's called this way, but this is an easy way to remember which direction it's supposed to rotate. It's supposed to rotate reverse of the Mark II. So it is supposed to go clockwise, and when you're looking at the direction of rotation, you have to be standing on the correct side of the pumping unit. So if you are standing right here where my mouse is, your right hand is on the polish rod, your left hand is at the pumping unit. You want to see which direction are those counterweights rotating, and they should be rotating in this direction. And a lot of times on these units, Mark II or reverse Mark, you will find an arrow, as we see right here, indicating, it's telling you that, hey, I'm supposed to be rotating in this particular direction. If you rotate it the opposite way, your gearbox loading is going to be significantly higher. So this is looking in on the cranks on some reverse Mark units. And notice how the crank holes do not go directly up the center of the crank. You can see that they're coming out at an angle right here. Same one for this one right here. This is another distinctive feature of these types of units to help you identify what type of unit it is. And now at this point, you might be thinking, wow, why are we going into such detail on these reverse Mark units? Why do I care? Well, you should care because you want to be able to identify the different types of units. They have different velocity profiles. So if you're doing a rod design, you would want to input that in there. That is going to affect the dynamometer cards and also the gearbox, the calculated gearbox loading and the calculated rod loading due to that different velocity profile of how it moves around through a stroke. But there's another reason that you want to be able to properly identify these, and this is going to be for position calculation methods with pump-off controllers. So if you have a POC that has this Hall effects sensor that is looking at a magnet rotating on the output shaft of your motor like this is a POC that is using the geometry of the pumping unit and the linkages to calculate the position of the horse head. So on these types of POCs, this is the preferred position calculation method for the Lufkin POC. Remember, a dynamometer card is load and position, and these types of POCs are calculating the position of where the horse head is. And in order to accurately do that, they need to have the correct pumping unit geometry. Otherwise, the dynamometer cards can become skewed, and you can have distortion in your dynamometer cards. Here's an example of distortion. I do not necessarily know what caused this. This is just an old picture I have. This is a downhole pump card that is not drawing accurately. It should not look like this. So there is something wrong in the calculation, and potentially it could be the wrong pumping unit geometry input into that POC, which is distorting the calculated position and throwing off these cards. So this is why we care about the different types of pumping units and identifying them. Of course, you want to do pumping unit maintenance, and where you're going to have most of your maintenance issues, it is going to be on your bearings. Just like as when you get to be old, where do you have problems? It's usually with your joints. And so the bearings are the rotating parts of the pumping unit. The walking beam is usually going to be in good condition for life. It is going to be these bearings where you have rotation occurring. So you can see something went wrong here with the equalizer. Here is one of the pitman arms, and you don't see the other pitman arm. This one, apparently that pitman arm fell off, but you can have issues at the equalizer bearing. You can have the wrist pin. From my understanding, this is usually where you have most of the maintenance issues. This is where it ties into the crank. Here's another wrist pin failure, and I really looked hard for this video. Somebody sent me this picture, and they said that this unit was running, and I was like, well, send me the video. And the pumper, when he pulled up on location, found this pumping unit running like this. It kind of looks like a dog peeing in a way, but it was only running with one pitman arm connected to the equalizer very, very slowly, but it was still doing its job. It was kind of a funny video. Unfortunately, I could not find it for you. Now, let's look at some different pumping unit geometries. So there are specialty type of pumping units. If you have wells that are dotted in some farmers' fields, and they have one of these water pivots that is rotating around in a circle, there are height limitations to the pumping unit you can have in that specific location. So you might need a low profile pumping unit that looks like this. It has a very low clearance on the height. And other than that, it's just kind of a weird geometry style pumping unit, but it's going to do the exact same. These are always kind of fun. You can see the wellhead is hiding down here in the cellar. So when you want to go down in there and tighten the packing for the stuffing box or install the dynamometer, you have to get down in the cellar. You better make sure there's no H2S gas. But this is a low profile pumping unit. It's always going to have a shorter stroke length. You're never going to have any super long stroke lengths with those types of pumping units. Here's another low profile one that you could have if you're in one of these farmers' fields. This is a strap jack, and it gets the name from this strap right here. And again, you can see this pumping unit is pretty much buried. Okay, and so I'm squatting down as I'm recording this video, and really these top bars right here protecting it were probably about, I don't know, 3.5, 4 feet high, and the whole pumping unit is down in the ground. The whole wellhead is down in the ground, but especially type of pumping units if you have vertical clearance issues. Here's another interesting type of pumping unit, and this is called a bent beam, or at least that's kind of the slang way of describing this one. And do you see why it's called a bent beam? Well, look at the walking beam. It is not straight, it's bent, and it has conventional counterweights here on the crank, but also there is some beam balance going on here. So these types of pumping units I've only seen up north. In North Dakota, Montana, I have not seen these make their way down south. I do not know what the brand is, but kind of an interesting style pumping unit right here. And I'm sure if you talk to a salesman there, they would say that due to this bend right here in the geometry and the linkages, you probably have a more uniform torque or something like that on the gearbox. Not exactly sure, but kind of an interesting style look to them. Here's another interesting pumping unit. This is called the grooves. Slang term for this is going to be the big wheel, and you can see why. It's got some big wheels, and I was thrilled to pull on location because I was supposed to check this well out, and I was just amazed to find this pumping unit running. I've never seen anything like this in my life, and I probably sat around there for about 20 minutes just watching it pump and taking videos. And this one has a dynamometer hooked up to it with a Lufkin type POC, and it was somehow calculating the position correctly, which I was also impressed with. But you can see it's got these big wheels. There are some counterweights right here on this wheel right here. But again, all kind of the same thing. They don't sell these anymore, so there's probably just some downsides to this relative to the more conventional style pumping units. But it's always interesting to see some interesting pumping units in action. So that is the end of looking at different style pumping units. And now we're going to look at the different components of a pumping unit. I want you to understand what these are if I mention these throughout the course. So this is a conventional style pumping unit right here. You can see the output from the gearbox is right here below the equalizer, so it's not a reverse mark. So here we have the motor, the prime mover, the energy source that is driving the system in the back. Then we have the belt guard, and this is covering the sheaves and the drive belts. So remember, we got the motor sheave, and then we have the gearbox or bull sheave that you can't see. It's hidden in here, and it's covered up to keep birds or other animals out to try and prevent them from getting caught up in those drive belts because the unit starts automatically. And so when critters get in there, they get ground up and mangled. But that is covering it here. Also, the cover here is to keep the drive belts out of the sun so they have a longer life. Here is the gearbox as we've looked at. We have the pitman arms that are connecting up here to the equalizer. and we have two different pitman arms attaching to either side. And on this equalizer right in the middle, we're going to have our equalizer bearing. This is what connects here to the walking beam. Then we have the saddle bearing right here in the center of the A-frame, the main support that the walking beam is sitting on. Here is our horse head. On this side, we have the bridle wire. Some of these components I'm going to show you on the next slide because they're hard to see right here. But we have the bridle wire cable right here, which is attached to the carrier bar. And sitting on top of that carrier bar is going to be the polish rod clamp. This is what's clamped onto the rod string. Our top rod is going to be the polished rod, and potentially we could have a polish rod liner, which slides up and down on that polish rod as needed. And this one does. You can see there's an increase in diameter right here. So this is the polished rod. Here's the polish rod liner. Here is the Samson post right here at the front of the pumping unit. We have the crank that is coming out from the shaft here on the gearbox. We have different crank holes, which we can pin it into to change the stroke length. We have the wrist pin right here, which is the most common bearing to fail, as I mentioned. And here are the counterweights, which we can slide up and down and remove and do whatever we want to offset the weight of the rod string in half of the fluid load. So when you look at a pumping unit, you should find a pumping unit tag. If it's not too old of a pumping unit, it should have one, and it will tell you what the pumping unit designation is. So for this one right here, this is a reverse mark, 912D 427 192. And if you want to know what these numbers mean, if you look in the upper left corner, on page 6 of my sucker rod pumping short course, my brochure, it'll tell you what the API designation means. So the first letter here is going to designate what type of geometry. So a C would be conventional, an M would be a Mark II. This number right here tells you what the gearbox loading is. So you'd multiply that by 1,000, and that would tell you how many inch-pounds the gearbox can withstand. D stands for double reduction is occurring in the gearbox. The structure rating of the pumping unit, if you take this number and multiply it by 100, that's going to tell you what the structure rating is. So for this particular pumping unit here, it can basically withstand, for the structure rate of the pumping unit, so the A-frame and the bearings, can withstand 24,600 pounds is what that means. And here's going to be the maximum stroke length of that pumping unit if you have it in the long hole. Okay, so here's some of the components we could not see so easily on that prior picture. So we've got the bridle wire, which is going up and wrapping around the top of the horse head, as you see in this image. Here is the polish rod clamp, and this is what's clamped onto the rod string, and that way it is supporting all of the weight, and it is sitting on top of the carrier bar. Okay, so the carrier bar is at the bottom of your bridle assembly. Now notice we have some load cells in this image. We actually have 3 different load cells in this image. This is the horseshoe load cell from Ecometer. Here's a load cell. This is a permanently mounted load cell from a POC. And this is a specialty type of load cell from a new style of pump-off controller sold by Amplified Industries, formerly known as acoustic wells. But essentially what we were doing in this test here, we were testing all these load cells to see what their outputs were in this particular example. But if you have a true load cell, it is going to be sitting here between the carrier bar and the polish rod clamp, and it's actually bearing the weight of that rod string. And so this is going to be the most accurate type of dynamometer that you can install. Now, if we look at this one right here, there's a few other components to mention. So you can see here we have the polish rod with the components we looked at. Here is the polish rod liner. It's got some bolts and you can slide it around as needed. And essentially you can either have a smooth polish rod with a polished face from top to bottom, or you can have just kind of a normal polish rod, which is not polished, but then you put this liner on there, and that's going to be a little bit cheaper of an operation. So this is the polish rod liner. Here is our stuffing box, the top seal on our tubing. And then there's also a rod BOP, which you can seal in. For example, if you need to change the packing in the stuffing box, it's got some lower packing that should seal off, so you can change the upper packing, but sometimes this is leaking. You can close in the rod BOP. These are also very common now, especially nowadays in the Permian Basin, because we have lots of wells that are getting hit by offset fracs. And so there might be a well that's half a mile away being fracked, and it breaks over through the reservoir up into this particular well, and it might start to blow out the stuffing box here. So if you want to keep pressure control off the stuffing box, which is the weak link on your tubing, you can close in the rod BOP. Now what's interesting with this image here is I actually took this picture because it was a kind of a safety picture. Do you see a safety hazard in this image here? And it's going to be up here at the top of the polish rod. And you can see right here, this coupling is just kind of teetering on the edge and about to fall off. So sometimes when they pick up the polish rod, the pulling unit does, and they're hanging the well on, they'll put on a coupling to pick it up because they put a rod on top and they later unscrew that rod, but they don't always screw this polish rod, or they don't always screw this coupling on very tight, and sometimes it can become unscrewed if this is rubbing on the horse head at the top of the stroke. I've seen this several times where it's just kind of hanging around there and it's just about to fall off. I've never seen it fall off, but certainly something to look at, because if that fell on your head or your shoulder, I can guarantee you that would hurt right there. But these are the components right here on the front of the pumping unit. Here's some videos just kind of looking at the back. So you can see our motor is driving our gearbox. And again, it's pushing up on the pitmans on the walking beam, causing everything to move up and down as it reciprocates. And here is another video. This is going to be of a gas engine right here. And you can kind of hear it, chugga, chugga, chugga. And with a gas engine, if it's out of balance, it's easier to tell because the speed changes more. This one's counterweight heavy. So watch as it tries to lift the counterweights, or listen. You can kind of see it slow down as it was trying to pick up those counterweights. Now it's going to speed up as the weights come down. I just always love the sound of a gas engine. Sometimes it's not fun to work around though. It's just like, oh, please be quiet. So that is the end of pumping units. Let's go a little bit deeper into sucker rods. So we talked about standard rods, and these are stick rods. Usually you don't even call them stick rods. They're just sucker rods, right? We have our steel and our fiberglass, but I put stick rod here in contrast to coiled rod. So if you've ever heard of co-rod or continuous rod or coiled rod, what it is, it's a rod string. It's all one rod string right here. It has two connections. So if you look at these connections here at the ends of our stick rod, we have our upset and our pins. Well, a continuous rod only has two connections, one for the very top, one for the very bottom. So these are kind of special. They're very specialty, really. They require specialty equipment, but they're becoming used and applied more and more, especially in deviated wells that have lots of rod-on tubing wear. That's the main application. They're also good for heavy oil. They were initially designed for heavy oil because when you look at the rod body, the upsets are going to be much larger in diameter. And so if you're pumping a very thick fluid, it's much easier if you have more clearance between the ID, the tubing, and that rod body, as opposed to the large upsets and the couplings at the end of the connections. Well, these only have two connections, one at the very top and the bottom. And at the bottom of the rod string, we will have typically sinker bars. Okay, so sinker bars can have a neck right here, which makes them easier to pick up with the rod elevators with a service rig, or they can just be full diameter, as we see in these examples right here. These are 1.5-inch sinker bars with some 3/4-inch couplings that also have an 1.5-inch diameter to them. But we typically put these on bottom because they're heavy, and they're going to keep some of the smaller diameter rods in tension, especially the fiberglass rods up the hole. You don't want those to go into compression, but also the large diameter resist buckling. And so there's not much weight at the bottom of the rod string, especially the bottom rod right above the plunger does not have much weight. It only has to carry its own weight. And so a lot of times it is going to be in compression, especially if you're pounding fluid or especially if you're tagging. And so these sinker bars are going to prevent the skinnier diameter rods up the string from going into compression, and also they more resist those compressive issues. So let's look at sucker rods in a little bit more detail. We can see some rods hanging up in the rod basket on this pulling unit right here. And these rods have some molded rod guides. You can see them right here and here. And it's hard to see, but if you see right where my mouse is, there's a lot of stuff going on here. This is going to be where the coupling is on these bottom rods, and there's a rod guide below and a rod guide above on most of these rods. So that's one rod. The second rod would be here, and the third rod would be hanging up here in the rod basket. Remember, for steel rods that are 25 feet long, if the rod basket's 75 feet high, you can hang 3 rods down from there. So the purpose of sucker rods is to connect the pumping unit down to the plunger. That is their main function. We just want them to connect, transmit the reciprocating motion, and stay intact and not have rod parts. That's all we're looking for. And we have fiberglass and steel sucker rods. So here's a steel sucker rod. Here are the end fittings for fiberglass sucker rods. Okay, so this one's not fully formed. It should have a wrench square on it. It hasn't been fully cut off with a CNC machine. But here is the fiberglass sitting inside the metal end fitting. Okay, so the fiberglass is strands of fiberglass in a plastic epoxy. And the way that it has an end fitting connected to it is you put the body in there and there's a glue. And that glue adheres to the fiberglass body. And then there is a wedge system. If you can kind of see in this glue right here, there's a wedge system that keeps that end of that rod body from pulling out. So these are called end fittings for fiberglass rods. Different manufacturers have different end fittings. So here's Endurance Lift. It has a 12 wedge system. Super Rod has a 3 wedge system. But when we look at sucker rods, remember fiberglass rods are 37.5 feet in my part of the world, and they're going to come in 1 inch diameter or 1 1/4 inch diameter. Okay, that's what you're going to find them sold as. Steel rods and sinker bars are both 25 feet long. Steel rods, you will see them come in 5/8 of an inch, 3/4 of an inch, 7/8 of an inch, and 1 inch. And sinker bars are going to come in 1 1/4 inch, 1.5 inches, and 1 3/4 inches, and sometimes you'll see 1 5/8 inches actually. So remember, these are much larger just for the bottom of the string right there. Now there's another type of rod that you've probably never heard of, okay? And I actually had a misconception on exactly what this is. Sinker rods. So you might not want to run sinker bars at the bottom of your rod string for a particular reason, or maybe you have a really deviated well and you're pumping down in the curve, something like that. So you have your pump at 40 degrees deviation. You don't necessarily want big fat sinker bars down there because they don't like to bend, and your pump is set down in the bend. And so you can run what's called sinker rods. So sinker rods, for example, you could have a 1 inch rod that has an undersized pin. So if you look at the rod, when we talk about the diameter, we're talking about the body. But you always have this big upset here where you have the upset bead in the shoulder of the rod and the pin. And then, of course, we have to have our coupling on here, which is at least going to be the same diameter as the shoulder. But this is going to be a large mass right here, a larger cross section than this. So if you want to run bigger rods on bottom, but you don't necessarily want the huge pins because they don't have to bear much weight, you can run sinker rods which have an undersized pin, which means you can have an undersized coupling, so it's not sticking out as far. I know, for example, Tenaris makes these, so you can look into that. So fiberglass rods, they are much lighter. They're very strong, and they're much lighter than steel rods, and they're also very stretchy. So for the same diameter, fiberglass is 70% lighter than steel, and it's also 4.2 times as stretchy. Okay, but what we're going to talk about later on in this course is typically if you're looking at a rod design, let's say it's an all steel rod design of 7/8 to 3/4. If you want to see what it looks like with fiberglass, there are no 7/8 inch fiberglass options. And so fiberglass has an undersized pin. So a 1 inch fiberglass rod has the same pin size as a 7/8 inch steel rod. And this is the same here. 1 1/4 inch fiberglass rod has the same pin as a 1 inch steel rod. So as a result of this, they have a larger diameter for the pin size, meaning that you can install a smaller rod box on them. And so often the rod box is going to be the largest diameter object on your particular taper, and so you can run larger diameter fiberglass rods in the same size tubing. So for example, if you have 2 3/8 tubing, the largest steel rod you can run in there is 7/8 inch, but you can also run 1 inch fiberglass in there. Okay, just due to that undersized pin. So when we talk about how much lighter they are and how much more stretchy, this is for the same diameter, but a lot of times when we're applying fiberglass and steel, we're actually using a slightly upsized diameter. So instead of 1 inch steel rods, you would probably simulate your rod design or look at your rod design with 1 1/4 inch fiberglass. So therefore, it's not going to be exactly 70% lighter or 4.2 times as stretchy. And one of the reasons that they run undersized pins, I'll talk about that later in the course, but one of the reasons that the fiberglass rod manufacturers want to run undersized pins is that they want a larger diameter because they want to reduce the amount of stretch. Fiberglass is so stretchy, so you can limit that by having a larger diameter to the rod body. So let's look at API steel rod grades. Now, API is the American Petroleum Institute. It is a standard setting organization. So basically what they do is they have standards for sucker rods and all sorts of other related things in the oil industry. But for example, they're going to say that we want all of our rods to be 25 feet long. They're going to specify how straight the rods have to be, what the upset bead's going to look like, what the wrench square, and so all the properties, the actual dimensions of that rod. They're going to specify that because they want you to be able to buy a sucker rod from manufacturer A, and you can mate that up with a coupling from manufacturer B. They don't want there to be any differences. They want it to all be made the same. They also have some specifications for the composition of the rod, so some of the alloying elements, if you want the rods to be API certified and fall within the category. And as we see right here, they also have some specifications for the strength of the rods for the different grades. So most of the rods sold in the United States meet API specifications, but they're not all API. I'll describe that here in a second. So if we look at the different rod grades here, okay, so for grade C, let's start looking at the rod grades. This is a low strength rod. It's the cheapest. It doesn't mean it's a bad rod. It's just not going to be as high in strength. So this is the minimum yield strength and the minimum tensile strength as set by API in order for it to be in this category. So what that means, the yield strength is if you put a certain amount of tension on a rod. This is pounds per square inch. So this is a stress on a particular rod. The grade C rod should be able to exceed the 60,000 pounds before it starts to yield, which means it's going to plastically deform. So if you put a certain stress on a rod and it's below the yield strength and you release it, the rod is going to go back to its original position. You did not plastically deform it. If you exceed the yield strength of that rod, it will be plastically deformed, and a certain part of the rod is going to neck down and have a smaller diameter. So that is when it starts to yield. Okay, when it starts to plastically deform, the tensile strength is where it's going to pull into two pieces. Okay, and so when we're operating wells, we never want to get close to the yield strength. Okay, we do not want to exceed that, I should at least say, because once you exceed that, you're starting to permanently damage your rods, and you're going to have failures that start to occur. So when the well is operating, we don't want to exceed the yield strength for sure, but you also don't want to exceed it if you're trying to unseat a stuck pump. So if your pump is stuck down in the seating nipple and you're yanking on it and you're beating on it, you wouldn't want to exceed that there because you could damage a whole rod string in the process. So if we go to the table here, this is also in my rod pumping brochure, you can see a grade C rod. The yield strength is 60,000 pounds per square inch, and the tensile strength is 90,000. Well, a grade K is the exact same right here for these properties. So grade K, it's also a lower strength rod, but it's more corrosion resistant. It has more alloying elements in it to better resist corrosion, but it has the same tensile properties as C does. So these rods right here work well if you have a shallower well. They're usually good up to about 4,000 to 5,000 feet, depending on the diameter of your plunger. But once you get beyond that, these rods are going to start to be overloaded, and you need to look at a higher strength rod, and that would be grade D. In grade D rod, this is kind of the standard rod you most commonly will see out here in the Permian Basin, especially on deeper wells, wells that aren't too shallow. And so this type of rod, it is stronger in the tensile properties than the C and the K. You can see we're up to 85 here and 115, where we're going to pull the rod into two. There's actually three different types of grade D rods. We have a D carbon, a D alloy, and a D special, and these are within the API categories. So API has certain specifications as to what the alloying elements or the varying quantities of alloying elements can be to be in these certain categories. Okay, now if you need a higher strength rod, okay, if you're pumping something really deep, you can use the high strength, and this is the minimum yield strength. So let me explain this real quick. So when it says minimum yield strength, API is saying it has to at least exceed this. And you might buy a grade C rod from a manufacturer that well exceeds this. It might not be 60, it might be 70, but API says it has to at least exceed this. What's also interesting is API has a maximum yield strength and a maximum tensile strength for these different categories as well that's not as commonly focused on. So if you have a grade C rod that has a really high yield strength, it might be out of the category because it's exceeding the maximum yield strength or tensile strength for that particular category. So these are just kind of buckets, and API says if you want to be an API rod, you have to fit within these categories right here. And a high strength rod is going to be for deeper wells with higher fluid loads, and it's going to be higher strength in general when it comes to tensile properties, but that does not mean it's a better rod or a better rod to apply for your particular wells. As we will learn later in this course, as you tend to go down here and increase the tensile properties of the rod becomes more brittle. Okay, so you're getting a trade-off where it's theoretically it's better at holding the loads, okay, but it becomes more brittle, and that might be bad because it's more susceptible to where if you have a pit on the rod or some sort of stress concentration on it, that pit is more likely to rapidly initiate across the plane here and create a fracture plane on that particular rod. So we're going to learn about that as we go through the course. And so a lot of people nowadays are trying to avoid high strength rods. And if you want to avoid them, you can look at using fiberglass rods because they are very high strength. Remember, this is the minimum set by API. Most of the manufacturers well exceed these particular properties right here. And what's interesting with fiberglass rods is that a lot of people apply them and some people hate them. Okay, and I don't exactly know why, but people have different experiences. Some think they're great. They significantly reduce the loading, your rod string loading. You can have a smaller pumping unit. If you apply them in a certain way, you can get additional over travel or plunger travel downhole. But some people think that they lead to premature failure. So another advantage of fiberglass, though, is that if you have a very corrosive well, they're going to perform better because the body of the rod does not pit like a steel rod does. So the fiberglass in the plastic epoxy is not going to pit, but of course our end fittings here are still steel and they can pit. So these are the API categories here. Now there's lots of non-API grades. Okay, and what that means is that it does not fit into one of these categories for whatever reason. It does not mean it is a bad rod. And also there's a lot of rods sold around the world where they are not trying to meet API specifications. So if you want to have an API rod, you have to be in the club. I think you have to pay like $250,000 a year. You have to have inspections at your plant. And also you have to make the rod according to their standards. And you might not necessarily want to do that. So there's, from my understanding, I think there's like 50 or 60 rod manufacturers in China. Right, and of course China manufactures everything for the world. And about 15 of those are API certified. The rest aren't. It doesn't mean that the others are making a bad product. They might be making something with slightly different specifications and they don't necessarily care about the API certification or want to spend the money for it or have the inspections in their plant. But again, there's lots of rods that are non-API, and they might be non-API. The whole rod might exactly meet API specifications, but maybe they have a different type of pin right here, a different type of threads. I know Tenaris has, I think, what they call a premium connection, and it's kind of a thicker thread here. The whole rod is API specification, except the design of the thread is not, and it requires a certain type of coupling to mate up with it, and as a result, that makes that particular rod non-API, but it does not mean it is a bad rod. So just keep that in mind. So let's look at sucker rods here. Again, we have steel, fiberglass, and sinker bars. Here are the main components of a steel rod. We have the rod body. Here's going to be the upset. Here is the wrench flat. This is what's going to be used to make the connections up and break them apart as you run the rods in or pull them out. Here is the shoulder of the rod and then the pin. And the rod box is going to screw right up here to the face, which is right here below the shoulder on this lower side. Here's our fiberglass. Here is the body, and here's going to be the end fitting. We saw how that's glued in there with the wedge system, and then we have our sinker bars on bottom. Here's what a connection looks like for a rod string. So you're going to have two pins that are screwing into a coupling. Here's what the couplings look like. This is a cutaway showing the pin screwed in. What keeps the rod string connected together is if you put enough torque on the connection, it creates a pre-stress right here in this pin that is pulling the two faces of the rod and the rod box together. And this is what keeps it together in its pumping operation. If you do not put enough torque on it, this connection can unscrew, and then eventually the bottom of the rod string or below that coupling will fall off, and you're going to have what looks like a rod part, even though it might just be the rods unscrewed. So there are two different couplings as specified by API. We have a grade T coupling. This is a softer type of metal. And then we have a spray metal coupling. And a spray metal coupling is a grade T coupling, except they shave off a little bit of the exterior and they put on a very hard surface finish that is going to be nickel chromium. And this hard surface finish here is good for corrosion. It's also good for preventing wear on the coupling, but when you have a very hard surface finish here, it might prematurely wear your tubing down because this surface is harder. So if you have rod-on tubing wear with spray metal couplings, it might prematurely wear your tubing down as opposed to wearing the coupling down. And so you have to decide what is the appropriate coupling for my particular well. What are the problems am I having? Am I having box breaks or tubing leaks? And preferably we would prefer to have a rod part before a tubing leak because it's cheaper and easier to fix a rod part. We don't have to pull the tubing out of hole. So let's look at some common rod designs. This is a typical taper design for a rod string. So you're going to have larger diameter rods on top, and then you taper down with big sinker bars on bottom, as we've seen here. And the reason you have larger rods on top is that they have to carry more weight. This top rod has to carry the weight of all the rods beneath it, plus the fluid load on the upstroke. Well, this rod right here only has to carry the weight of the rods beneath it, plus the fluid load. So you can taper down, and you have to have the bigger rods on top because they have more stress on them. So this is a pretty common design here for all steel. Here's some other common designs you might see. You might see a rod design that has fiberglass, then steel, then sinker bars, or maybe you don't have sinker bars, you just have an all steel design and it just tapers down. Let's say that's 1 inch, 7/8, 3/4, and then you go up to 7/8, and maybe you don't have sinker bars. Quite common to see that as well. Here are two unusual and kind of specialty rod designs. So this would be an all fiberglass sinker bar rod design, and I have one customer that runs these exclusively because they're trying to get over travel. They're pumping the well hard, and with this design, if you pump a well fast, they might have 192-inch stroke length at surface, and they're getting 240 inches of stroke length down hole. The other reason they do it is that this rod design is pretty robust in dealing with corrosive conditions. So fiberglass holds up well in corrosive conditions. And also sinker bars, since they have such a large diameter, there's more metal that can wear away before you're going to have a rod part. But it's a specialty type of rod design that you would typically only see in the application I just mentioned. But so for example, you might have 4,000 feet of fiberglass, and then you might have 1,000 feet of sinker bars. Kind of an interesting design. This one right here is going to be a scenario that you might see if you have a well that's got the pump set somewhere down in the curve. Okay, so typically we don't put our sinker bars down in the curve. You might set your sinker bars right there around the kickoff point, but then as the rods go down into the curve and your pump is set down here, you're going to put some smaller diameter rods, probably with some rod guides. So maybe that would be 7/8 inch rods with rod guides down here, because sinker bars don't like to bend. So if we're going to put the pump down in the curve, we don't want a stiff assembly down on bottom that doesn't want to bend, because our rod string has to bend as it kicks out into the horizontal right here. So this is typically kind of what you're going to see when it comes to rod designs. And rod guides are quite common on rods, and the purpose of rod guides is to sacrificially protect both the rod and the tubing and prevent premature failures due to rod on tubing wear. And this is especially true in a lot of our modern wells nowadays, especially in these unconventional plays where we have pad drilled wells. So you might have 4 wells lined up on one pad, and they go down and then they kick off away from the other wells. They straighten back up. Here's where the pump is set. Around 10,000 feet, and you can see here's the kickoff point where it starts to go off into the horizontal. But these deviations right there are going to create a lot of rod on tubing wear. And so at certain points you might need to have rod guides, and the function is to sacrificially wear away and to prevent the rods and tubing from rubbing on each other and to extend the run life of both the rods and the tubing. If you have lots of deviation like this, you might get cards that are looking like this, and we'll talk about this. This is a card that indicates shallow friction, meaning that there's some friction higher up on the rod string that's not properly being accounted for with the one-dimensional wave equation. And the indications that it's not properly being accounted for is the distorted shape of the downhole card. And you can see the shallow friction effects in these slants occurring right here. Also, there's some distortion. That's not how a pump card should look, but this can happen when we have a lot of these deviated wells here. And of course, this is going to lead to accelerated failures. So here is a jointed tubing with a split. This is where the failure was. We were talking about it in a failure meeting. This is where the rod box was rubbing up and down at some deviated point here. Notice how much more pitting is occurring right here in this wear track as opposed to outside of it. You can see some corrosion going on, but significantly more pitting is occurring right here in this interval. And so there's different types of rod guides. So we have snap-on rod guides, which you can apply in the field. And these are not really used much anymore because they don't have strong retention force. And so they just start sliding around on the rod. Almost everybody is using molded on rod guides, so these have to be applied at the factory. And this is some type of plastic or polymer material, and they put some sort of clamp around the rod, and they have an injection mold, and they inject this onto the rod. And when the material is hot, it's expanded, and as it cools off, it starts to shrink. And this is what creates the really strong binding force between these molded rod guides and the rods that they're clamped onto. So this is typically what you'll see. That's what you're going to see right here. You can also have some specialty type of guides. These are roller guides right here. This would actually go in the place of a coupling. So you see these couplings here. Instead of having a coupling, you could have a roller guide between the rods, and they have these wheels, which would be ideal if they worked well, because instead of just having constant friction rubbing up and down, you could have a wheel rolling to try and reduce the amount of friction, but you never see these used. And from my understanding, the wheels break, or they get solids in there and they get stuck, components break off, they start falling down, and they create issues. So maybe in certain applications, like maybe in a slant well, you might try to use these, but I don't usually see these used, so I assume they're not working very well. Let's look at the components on a tubing string. So we've seen our tubing. Here's an example of a gas separator that's sitting on the racks by the tubing. It's oversized. You can see it's a larger diameter, and it has these slots cut into it. This is where the fluid is going to enter into the gas separator. So remember, tubing's about 30 to 33 feet long. This is how you're going to make a tubing connection up. So on the bottom, so on the top of the tubing, you'll have a collar, and on the bottom, you're going to have some threads or a pin, and you're going to stab one joint into the collar of another, and then you're going to screw it together with the rod tongs. At the very bottom of the tubing, you're going to have a seating nipple if you have a rod insert pump. In the seating nipple, it's just 1 foot long. And a lot of times, if I talk about the depth of the pump, I might be talking about the seating nipple depth. I've already done that in this section. And that's because that's usually where the pump is set. So that's talking about the depth of the pump. But this specialty seating nipple right here is just 1 foot long, and it has a little taper to it. And this is what the pump is going to be sitting down into if it's an insert pump, which is the most common type. Now here is a seating nipple, and here is a hold down. This is on the bottom of the barrel. Okay, and this is a cup type hold down. It has these 3 cups right here, these plastic rings, and it has a no-go. And this is what stabs into the seating nipple. This is a seating nipple that has a lot of corrosion on it right here. So this is going to create the pressure seal at the very bottom of the tubing, and this is going to prevent fluid from leaking out the bottom of the tubing, assuming that you have a good pressure seal. On this one, there was so much corrosion, and you can see kind of striations going down as the corrosion started to eat away, and this is what caused the tubing leak on this particular well. But this is going to be at the very bottom of your tubing string, and your full column of fluid in your tubing is going to be sitting on your downhole pump and your seating nipple. And remember, if your tubing is unanchored, it is going to move up and down. So on the upstroke, the rods pick up the fluid load. And when they pick up the fluid load, they're taking it off the tubing, so the tubing contracts. And when it contracts, it will buckle helically, and you're going to have increased contact at these points here with the bottom part of the tubing and your rod string. And this is going to lead to increased rod-on tubing wear, and of course associated failures. And then on the downstroke, when the plunger pushes the fluid load back onto the tubing stretches. So the reason we don't want the tubing moving is it's going to increase rod-on tubing wear, but also the plunger and the barrel are moving up in the same direction. And so effectively your downhole stroke length, the effective portion of your downhole stroke length, will be reduced if your tubing is moving. So we don't want that. So we run a tubing anchor. Okay, and it could be a tubing anchor or a tubing anchor catcher. This is typically what is run, and that's going to be abbreviated as a TAC, and this is what it looks like. So if you look at this TAC, you will typically run this somewhere down close to the seating nipple, except you might keep it above your perforations, as we mentioned. But the components of it are, it has a mandrel with an outside cage. It has these drag blocks right here, and these are the slips. And so you run this down on the bottom of your tubing, you rotate the tubing to the left, usually 7 turns. That is going to cause these slips to come out and engage into the casing. Okay, you have these really strong slips that are biting into the casing. After you engage those, you will pull the top of the tubing up. So you're going to pull it up in tension and then drop the slips at surface. And now your tubing is held in tension, and it's not going to reciprocate or move up and down with the addition or removal of that fluid load. So TACs are very important. We can see these on fluid level shots, as I mentioned. Also, they're the most likely thing to get stuck on your tubing string because they're larger diameter. So sometimes you might run what's called a slimline or slim hole tubing anchor, as we see in this image right here. So it's got more clearance for both solids to fall down and also for gas to flow up, because TACs can lead to gas interference. So you can kind of see the slips right here are kind of, they're kind of protected with this housing, but we have more flow path. Also, the drag blocks have been moved down underneath to try and increase that flow area around there. But the downside of these is it reduces the internal diameter. And so you have to be careful on where and how you apply these. We'll talk about that in the gas in solid separation section. So let's talk about gas separation real quick, because it is so incredibly important. If you have free gas that gets up into your pump, so here's our traveling valve and standing valve, our pump chamber. If that free gas gets into there, it's going to create both gas expansion, as we see here in the card, and gas compression. And really, it's usually the gas compression that's the most significant. If we look at this one, there's a little gas expansion, a lot of gas compression. And on these strokes, you're losing about 50% of the effective downhole stroke length. Okay, so instead of moving 100 barrels of fluid per day, if this was the average stroke here, it would only be moving 50 barrels of fluid per day. And so it dramatically reduces the efficiency of your system. So we install a gas separator at the bottom of the tubing. So this right here is going to be a simulation. This comes from Ecometer's gas separator simulator, and you can download this for free on their website, and you can plug in info on what your separator is and also your production rate and run a little simulation, and it shows you what's happening. But on the upstroke, as fluid is pulled in here, the fluid is sucked in to the gas separator. So you can see it's getting sucked down every upstroke, and the gas is naturally trying to bubble up and out due to lighter density. But if there's not enough time for the gas to bubble up and out, you can see right there, we just sucked gas into our dip tube. And once it gets into the dip tube, it is going to be forced to go up here, up through our pump. And when it goes through our pump, the free gas, we're going to see gas compression. So this is the importance of understanding downhole gas separation and how to remediate it. And that's why we have a large section on that in this course. So here's the wellhead. Okay, if you don't get out to the field much and you don't understand these components, let me quickly show you what's going on. You can see our pumping unit, our carrier bar, here's our polish rod and polish rod liner. But right here, this is a well that I was the company man on, and we were just about to turn it on production. That's why everything's nice and clean. We don't have an oil coating on anything yet. But this is going to be the surface casing. So they drilled down about 500 feet and they set casing to protect the fresh water. And then this is our production casing right here. So if you can imagine, this was a 4.5-inch casing coming up right here to our casing bowl. And then we have our tubing that is coming up through that right there. So the tubing's coming inside the production casing, and the gas that is produced is going to be coming up in this interval right here. This is called the annulus. This is the area between the outside of the tubing and the inside of the casing. It's called the annulus, or the backside. So the gas that's produced is going to come up here on the casing side, and it's going to meet at the flow line. The fluid that is produced, remember, we want good downhole gas separation, so only liquids producing up our tubing. They're going to come up here and they're going to meet with that gas and go down the flow line. You can see there's a test separator over here. But if we look at some of the different components here, so on our tubing, we've got our pumping tee. Okay, and it creates a T, that's why it's called that. Here is our stuffing box. This is the circulation loop on this side. So if you wanted to, for example, circulate some chemical, maybe the well's got some bacteria issues and you want to kill that bacteria, or you want to put, I don't know, some sort of paraffin solvent in there and circulate the chemical, you could pump it down the annulus, and then you could shut these valves and turn the pumping unit on, and all the fluid that's produced up is going to circulate back down hole to give more contact time with that chemical right there. So that's the circulation loop. It also gives you the ability to take samples off to look at what's being produced up or look at pressure. And of course, we have our valve here. This is where we would tie on for a fluid level shot, or a pump truck would tie on to pump some fluid down the well. This is going to be our production loop. So every well's got a production loop. Some wells have a circulation loop. They sometimes do not have that. But on the production loop side, the fluid's going to come up. It's going to move this way. Here is our back pressure valve. This is going to allow us to hold back pressure above what the flow line pressure is. So if the flow line pressure is 50, we could hold this at 100, 200, 300, whatever we want, based on how much we screw in this back pressure valve. And this is a check valve. Okay, and so the check valve is, as it's shown here in this image, both of these check valves are designed to only let fluid or gas move from left to right. And if something wanted to flow this way, it's going to shut and prevent that from happening. So for example, if you had a tubing leak and your tubing went under vacuum, okay, it could start to suck everything out of the flow line, even from far away. It could start sucking everything out if it did not have a check valve, because there's higher pressure on this side than this side, so fluid wants to flow, but the check valve should shut it off and prevent that from happening. Now, this check valve is not as important as this check valve. So remember, there's only supposed to be gas coming up the casing. But if you have a leaking check valve, the fluids that you're producing up the tubing can then come through this leaking check valve and start to circulate back down hole. And that's not what we want to do. Okay, we want to get that fluid to the tank. So this is the most important one. Sometimes you will find this leaking or heavily worn out and circulating a lot. And sometimes you can actually see that on fluid level shots. We will talk about that in this course. But here are the just kind of the main components. I guess the only other thing to mention is that you have your valves coming off. You always have your primary valves coming off your casing and your tubing that you can shut these off if you need to do any work on anything here on the wellhead. So let's talk about controlling runtime. All right, so there's different types of timers. If you have, let's say that the production capacity from your well or your pumping system is 100 barrels of fluid a day, but if the reservoir will only give you 20 barrels of fluid per day, we need to reduce the capacity. And the easiest way to do that is to put it on timer. So instead of running the well 100% of the day, maybe we only need to run it 20% of the day to match the amount of fluid coming into the well. We can do that with timers, and there's different types of timers we'll talk about. For example, this one's set on 80%, meaning it's going to run the well 80% of the day. So we want to match the amount of fluid coming into the well with our timer. Now you can take that to another level, a higher level. These are kind of dumb and basic, and they're great, but you can take it to a more advanced level and have what's called a POC, or a pump off controller. And a lot of times they're sold now as rod pump controllers, and RPC, but this is typically how we refer to them out here in West Texas, and that's the terminology I will use. But a pump-off controller is a permanent dynamometer system, and it's drawing dynamometer cards for every stroke, and you have a certain fillage set point, and so you can tell the pump-off controller if the fillage in the pump downhole gets below 90%, turn the well off and go to a predetermined amount of downtime. For example, 20 minutes. And after 20 minutes, it'll turn the well back on, and it's going to monitor every stroke and shut the well down based on the pump fillage. Also, the load cell allows us to turn the well off. For example, if we have a load violation, if the rod string jumps off the pumping unit, okay, that's going to violate the minimum load. So that is what the pump off controller does. Now we can take this to another advanced level, and we can integrate the pump off controller, which is shown right here with my mouse, inside of a variable speed drive, sometimes called a variable frequency drive. Now, instead of just shutting the well down if the pump fillage gets too low, if you integrate it with a variable speed drive, you can now slow the strokes per minute down. So if the pump fillage is getting too low, if it's moving with my mouse from right to left, instead of just turning the well off, now we can slow the well down and we can try to get the pump fillage back higher. Sometimes if you produce lots of solids, you don't want to shut the well down because all the solids coming up the tubing are going to fall down the tubing on the top of your pump, and you might stick the plunger the next time you start it up. So that's one common application for variable speed drives. Also, just the ability to easily adjust the strokes per minute by changing some of the settings right here is quite nice. So this is some of the automation we will talk about also later on in the course. And that is it, my friend. That is the end of section 2. Here's a nice silhouette of a pumping unit after a long day, a long summer day up in Montana. So, up there in the summer, the sunlight's like 16, 17, 18 hours, actually, something like that. You can work as long as you want. And I had a long day, and I was trying to catch some shade, and I was standing right there, and I said, wow, that's actually really beautiful. Let me make a video. So in the next section, we're going to talk about optimization. What is optimization? And I'm going to show you some examples of some things you can do. And we're going to get a feel for what the fluid level gun and dynamometer system can do. So I'm going to kind of get your feet wet before we jump off into fluid level shots in part 4. So I'll see you in the next section. Hey, what did you think about that video? I thought it was fantastic, and if you thought that was interesting, you should strongly consider taking my online course. So if you go to rodpumpingoptimization.com, it will link over to it. And we're going to be talking about all sorts of good things, and you can see the quality of the videos. I've been working on this for 4.5 years. We're going to talk about fluid level shots, dynamometer test, gas and solid separation, different components of our downhole pumping system, automation, how do we diagnose failures, and even chemical treatment. And really, it's all about troubleshooting and optimization, and that's what we're focused on. So we have to have the feedback from the well that we're getting with our diagnostic tools, but then you have to integrate that into your knowledge of the system, which I'm going to teach you all about. So I strongly recommend, if you are interested, go look at my course, look at the outline. So I have some videos that are free here on YouTube to watch, but you can find more free videos if you go to rodpumpingoptimization.com and sign up for the free preview. But I actually recommend that you buy the class. As you can see from the quality of the slides and the presentation you just watched, it is an excellent class. So I look forward to seeing you there.